Okay, so it's about that time of day. Let's go ahead and get started. Let's start with our usual announcements. So just a reminder that you have homework due tonight. That's in the usual WebAssign. And then just about a half hour ago, I released our quiz 7. And just a reminder that that is due tonight at 5 p.m. in OneNote. And so I wanted to just start by briefly talking about, again, how you submit your quizzes. Okay, so let me go back over to Sakai. So the easiest way to submit your quiz will be to log into Sakai, and then in the bottom left over here, there's a link called OneNote, and it'll ask you to sign in. You should sign in with your Wake Forest email, and you'll end up with a different screen, but it should take you to a notebook, a OneNote notebook, and you won't see everybody's, you'll just see yours. And you should have 3 sections in yours, so let's just look at Nick's. And what you'll be doing is you'll be going to the quiz sections, and you'll be creating a page in there. So maybe there's one already made, or maybe you add one, doesn't really matter. And just title it Quiz 7. And then you'll write out your answers however you want, preferably on like a blank piece of paper or on a printed out version of the quiz. And then what you'll do is at the top, you go up to Insert. And then I'd prefer that you submit these things all as PDFs, just because that's like a nice format. JPEGs or image files look kind of bad. And so the easiest way to do a PDF is to insert as printout. And it'll ask you to go find the file. And if you're scanning with a cell phone, I recommend, or I would really prefer that you use an app like Adobe Scan. Okay, so I put a lot of this in my announcement, but I'm just reminding you. Do you guys have any questions about how you're going to be submitting your quiz today? No? Everybody seems all right with it? So I will be available after my last class at like 4:50 or 5 if you get stuck and you need help. All right, so that's quizzes. Then just a reminder that exam 2 is next Monday, so it's getting closer. And we will be doing a review session on Friday via Zoom. But remember, there's also the practice exam I sent out last week. Well, it's kind of like a couple practice exams all mushed together. So you can try working through that for practice. Other things you can do are I posted a link to some videos that were made by another professor, Jason Parsley. You could try watching those if you had certain sections you felt you needed to brush up on. Okay. Alrighty, so any like administrative questions so far, like how things are going to work? If not, we'll just get right into it. Because really, today is what I consider one of the, slightly tougher sections in the whole course. And it's not that any individual part is hard, it's just that you're putting a whole lot of things together. So what we're really talking about today is section 3.5, and it's also a little bit of 3.6. It's kind of essentially the same thing, except you can use a calculator for 3.6. And really it is like, given an equation of a function, how do you get like a somewhat accurate or qualitatively correct sketch of the graph? And the book has this long thing of guidelines. I've tried to sort of narrow it down to, in my mind, like what the 4 important parts of that are. And, along the way, you end up getting just about everything the book gets. So it's just sort of another way of doing what the book does. But the way I'm trying to phrase it is like this. So here's basically the list you're going to go through when you're sketching a graph. And I've put them in the order so that as you do them, you get sort of a more and more accurate graph. And yeah, just a reminder, we do have a TA in chat, so if you have like a quick question, you can. She might be able to answer it in chat. Yeah. So the first thing is symmetry. Like, is your graph symmetric at all? And we talked a little bit about symmetry, and I put it in my video about what symmetry is about. And so really, we only are really talking about two types of symmetry here. Is the function even, which means it's like, if you fold it over the y-axis, it matches up. So it's reflective across the y-axis. Or is it odd, which is sort of like symmetric about the origin, or you can think of it as kind of being two reflections. Or a lot of functions are just not either of these, in which case it's not self-full. So I put this as number 0 because it's sort of like an optional thing. Like, just if you happen to notice that the function's even or odd, it can help you, save you a little work, or just help you verify, like at the end, does my graph actually look like, if I reflect it over the y-axis, it's actually the same, that sort of thing. So it's a good thing to like notice, but if you go through all the work, you'll end up getting an accurate picture anyways. The second part that we're going to be working through is what I called intercepts and easy values. We're more going to be concentrating on the intercepts part of it. It just happens like there's functions where you might be interested in certain values that you could just plug in. So here I really mean like, what are the x and y intercepts? And this helps you just get a few points on the graph. Second, what you'll do is you'll look at the equation and you'll try to determine all its asymptotes. So like, are there any vertical asymptotes where it goes off to infinity? What happens really far away from the origin, like really far to the right or the left? Those are the horizontal asymptotes. And occasionally there's like a slant asymptote, which is also kind of saying, if you go far to the right, what happens? Maybe it doesn't approach a horizontal line, maybe it approaches a slanted line. So that's kind of what I mean by asymptotes. And what I mean by behavior at asymptotes is like, how does it approach those asymptotes? Like, does it, for a vertical asymptote, does it go off to plus infinity or minus infinity? For a horizontal asymptote, does it approach from above or below? That sort of thing. And then once you've kind of added your asymptotes, you go through and you look at like, what does the first derivative of your function tell you? And basically the things it tells you is, are there any local mins or maxes? And where is your function increasing versus decreasing? Okay. And then once you kind of understand the first derivative, then you move on and say, what does the second derivative tell you? And that helps you tell like where the function is concave up versus concave down, how it's curving, and any inflection points where it switches concavity. Okay. And so kind of once you've done all this, then you try to put it together into a graph. You try to draw a picture of a graph that has all the properties you wrote down. Okay, so that's what we're going to do today. And these examples are fairly long, so I have a feeling we might only get through 2 of them. But I have some videos with a couple more of them if you want to watch those. Okay, so let's just jump right into an example, because I feel like, yeah, that's the best thing for us, is just see how this works. Okay, so our first example is we're given this rational function f. So it's x squared minus 4 over x squared plus 2, and we're asked to sort of give a sketch of it. And here, because taking derivatives of a quotient like this can be pretty tedious, I've saved us the work and I've already computed the derivatives here. So here's the first derivative and here's the second derivative. That'll just save us some time. Okay. And then we're going to graph it here. Okay. So let's remember, our first step here is, so let's remember, what's the function? X squared minus 4 over x squared plus 2. So the first question might be, is this function symmetric at all? Okay. So if you think about it, the only way we really have to tell whether f is symmetric is we have the definition, right? So the definition of symmetric would be, well, I mean, even or odd is that type of symmetric, is what happens when we plug in minus x. Does it come out to be the original function? Does it come out to be the negative of the original, or neither? And so here, if we plug in minus x, we substitute that in everywhere. That was the correct function, right? Yeah. So if you plug in minus x everywhere, well, you just see that the squares just kill all the negatives, right? So this just ends up being, exactly what we started with. So this means, so another way of saying that is that if you plug in minus x, it can be simplified to just being the same as plugging in x, and so this means f is even. So that means whatever graph we end up with, it's going to be symmetric over the y-axis. Okay. So in principle, really all we would have to do is figure out what it looks like to the right of 0. But so yeah, let's move on. So that's symmetric. That's one's kind of optional. Number 1 was, let's check, we're mostly going to concentrate on intercepts. That's not how you spell intercepts. So let's check the intercepts. So the x-intercepts, right? So that means where it hits the x-axis. So that happens when y is 0. So we're trying to figure out where is the output equal to 0. And really that's saying, where is our function equal to 0, right? Well, if you think about it, the only way a fraction can be 0, like this, is if the numerator is 0. So this really means x squared minus 4 has to be 0. And so x has to be either x equals 2, or x could be minus 2. So remember, these are both combined with the fact that because it's an x-intercept, this will be y equals 0. Right? So those are the x-intercepts. If we go ahead and put these on the graph up here, we found that we have the points 2, 0 and negative 2, 0. So let's go ahead and put those on the graph. So we have 2 points on our graph now. We know 2 points on it, just kind of the point. And y-intercepts, oops, let's go back to black. That is saying, where does it hit the y-axis? So that happens when x is 0. So what is f of 0? And that's just, if you look at it, if you plug in 0, you'll end up with minus 4 over 2, which is minus 2. Right, so this gives us the point 0, minus 2. So if we put that on the graph, it was minus 2, right? Yeah. So that means it's down here. Okay, so now we have 3 points on the graph. Okay. Okay, and that was sort of the easy part. So, now let's move on to the stuff that tends to get a little bit more confusing. So number 2, I'm saying find the asymptotes. Okay. And so for us, there's really three types of asymptotes. There's vertical asymptotes, horizontal asymptotes, and slant asymptotes. So let's do these one at a time. And maybe I should write out these words. So let's first do vertical asymptotes. Okay. So if you think back to when we talked about like limits and stuff, how did we notice that a function had a vertical asymptote? It was essentially when you have like a number that's not 0 over 0 when you plug in a certain number, right? So that means we look at when is the denominator 0. So when the denominator is 0 and you have to be careful because if the numerator is also 0, then you don't quite know what's going on. But if you have a case where the denominator is 0 and the numerator is not 0, that'll be a vertical asymptote. So here that'll be, we're basically asking the question, for what x values does x squared plus 2 equals 0? If you look at this for a minute, you'll realize that there are no solutions. So there are no vertical asymptotes here, which is nice. Okay. For horizontal asymptotes, well, those were what we were just learning about last time. And so remember, the way you tell what the horizontal asymptotes are, at least the way I showed you last time, is you just consider what's the limit, what happens as x gets really big or really big and negative. So we compute the limits at infinity. And if you think about what we talked about last time, you could do the multiply by 1 over x squared here trick, or you could recognize that the numerator and the denominator have the same highest power, x squared. And so the answer will be the ratio of their leading coefficients. So this will just be 1. And if you were to take the one at minus infinity, it'll be exactly the same. This one's also equal to 1. Okay, so what that tells us is that y equals 1 is a horizontal asymptote. Okay, so this function does have a horizontal asymptote, and it is y equals 1. Everybody follow that? Okay, so let's go ahead and put that on our graph. We can fill things in as we go. So we said y equals 1. What color should we make asymptotes? Maybe green. So up here at 1 or so, there's a horizontal asymptote here, and we draw those as dotted lines, remember, to indicate that they're not actually part of the function. So this is y equals 1. Okay. And then the final possibility is, are there any slant asymptotes? Okay, so what do you guys think? Yes or no? Do you think for this function, will this have a slant asymptote? Just type yes or no in chat. What do you guys think? So type yes if you think it does, type no if you think it doesn't. No, I see a no. Okay, good. And you are all correct. So the reason there is none since the degrees are wrong, right? The only way a function can have a slant asymptote, at least a rational function, would be if the degree of the numerator was exactly one more, but here they're the same, so it can't happen, right? So that can be an easy way to tell whether there's going to be a slant asymptote or not. Okay. Something else that I think is worth doing is, when you're doing asymptotes, is answering the question, what is the behavior at the asymptotes? So basically what I'm trying to ask is, like, so this function only had one horizontal asymptote and no vertical ones. What I'm saying is, like, as I go really far to the right, is it going to do something like, is it going to come in from above or is it going to come in from below? Like, which of these cases is going to happen? And how can we tell that? And like the same, like, which way is it going to happen in the left? So that's what we're trying to figure out here. And you may look at this function and say, well, I don't know how to tell that, but let me show you a trick for telling that. That works for horizontal asymptotes. So for, let's just erase it. So for horizontal asymptotes, so for the horizontal asymptote y equals 1, we go back and we do polynomial division. Some of this stuff you can also tell from, like, where the function's increasing or decreasing, but sometimes it's good to have like a second check on things as well. And I want to show you this technique at least once. So if we do polynomial division, our numerator was x squared minus 4. Our denominator was x squared plus 2. And we would see that, you know, x squared goes into x squared once. So we would get an x squared plus 2. We would subtract, and we'd be left with minus 6 here. So this tells us that the function we started with, just another way to write it, we're not actually changing anything, is that it went in exactly once, and then it has some left over. Okay. And the reason why this is nice is, now think about what happens when x is really large. So when x is very large and positive, well, the 1 is just 1, but the second bit is this part is negative. Okay, so what that's saying is, as you go to the right, this function will be equal to 1 minus a little bit, right? Because it's negative. And so if you think about that on the graph, if your outputs are a little bit less than 1, then that means it'll be below the green dotted line, right? So it'll actually be this lower one. And you can do the same thing on the other side. When x is very negative, so very far to the left, this part up here is still negative, right? Because the square gets rid of the negative. Okay, so this is always negative, right? Because, you know, there's no way the x squared could ever be negative. And so it turns out that on the other side, it does the same thing. So that means we can erase this top one again. So it'll be 1 minus a little bit. So it'll come in from below. Okay. Though it turns out, like in this case, we could also have skipped this step and gone directly to the first derivative, and it would end up telling us this as well. But it's good to have multiple techniques for any given thing. Okay, so that was asymptotes. Did anybody have questions about like finding asymptotes so far? And what number are we on? This is like 2 maybe? No, it's got to be 3. Okay, so 3 is, we're going to see what does the first derivative of this function tell us? Okay. Let's copy the first derivative. So that was given in the problem. So the first derivative here is 12x over x squared plus 2 squared. Okay. And if you remember back to when we were doing like the first derivative test stuff and the increasing, decreasing stuff, you know, one of the things we were interested in was critical points. So here we're going to try to do like the number line method where we try to figure out where could the sign change and then figure out what that sign is in each region. And so the easiest way to do that sort of in general is to figure out where is the derivative 0 and where is the derivative undefined. And some of these ones that are not defined, they might not actually be critical points, but we still need to find them. Because they could be asymptotes, and like the sign of a derivative can switch at an asymptote. So in the first case, this would just be asking, where is 12x? Where is this equal to 0? Well, that's exactly when the numerator is 0, right? The denominator can never make anything 0, so this can only happen if the top is 0, which means x had to be 0. In this formula, the only way the derivative could not exist is if the denominator was 0. And if you think about that, if you square root both sides, you get that. And so this has no solutions. Okay, so you don't get any from there. So there's only sort of one point we have to put on our number line, the x equals 0. Okay, so we draw our number line. We put x equals 0 on there. And then remember, what we're trying to figure out here is the sign of the derivative. Okay. So we might pick like a test point in each region, like maybe 1 and -1. And say, well, if I look at my derivative up here, if I plug in, say, 1, it'll be positive over positive. If I plug in -1, it'll be negative over positive. So this one would be like, so overall that's a plus. Overall, this one's a negative. Okay. So essentially what that tells us is, you know, the function's going to be going down and then up here, right? So it tells us that this is going to be a local min. Right? Okay, so that's sort of like all the information about the first derivative is kind of encapsulated in this little diagram, which is kind of why I like to do that. So what we've learned is, you know, on this part, this is the decreasing region. And over here, remember f is increasing on here, right? Because the derivative here was positive to the right, and to the left it was negative, so it was decreasing. And we'll use that information a little bit later. But one thing we can say on our graph now is that this x equals, at x equals 0, we said that was a local min. So that means here, we know that this is going to have to go up a little bit on both sides because it's a local min, right? I'm making it worse. Let's try that a little bit. So we don't want to draw it too far because we're going to have to link it all up later, but it just helps us keep track of all the information. Okay, so that was the information about the first derivative. As you can kind of all summarize it all in a diagram like this. Okay, any questions about first derivative stuff, guys? Alrighty, well, if there isn't, then let's go ahead and try the second derivative. This has got to be what, number 4, I think. The numbers aren't so important on these. Analyze. So let's analyze the second derivative now. That'll give us even more information. And so let's copy down what the second derivative actually is so we can analyze it. So it gets a little more complicated. It's 24 minus 36x squared over x squared plus 2 now cubed. Okay. And basically what we do is we do exactly what we did for the first derivative, but now just all the names for things change, right? So we don't have any critical points. We're just going to figure out, because we're really looking like where is the second derivative positive and where is it negative. And so the easiest way to do that is to find the points where it's 0 and or maybe or is a better word here. Or the second derivative just doesn't exist, isn't defined. Okay. So the places where it's 0 would come from solving this. Which means we would have to have the numerator be 0 again, just like before. Okay, so let's do that. Divide through by 36. And let's see, those have a common 12, or a 12 in common. So that can be reduced to 2/3. If we square root both sides, we get that x is either the square root of 2/3 or it's minus the square root of 2/3. Okay, we get two solutions whenever there's a square, usually. Okay, so these are our 2 points where the second derivative was 0. If we were worried about where the second derivative didn't exist, well, we would be looking at, again, when the denominator is 0, because that's the only way it could, something could go wrong, not have a point in the domain, right? And so you would ask yourselves, is it ever possible for this to be 0? And if you cube root both sides, you would see, well, no, there isn't. There's no way, maybe an easy way to see it is there's no way that something squared could be negative, right? So there's no solutions here. Okay. And so now when we draw our number line, there's 2 points on it. So there's minus square root of 2/3, and there's the positive square root of 2/3. And now we want to test the second derivative in each derivative, right? Because we're here, this diagram is describing the sign of the second derivative, which will tell us about concavity and inflection points. Okay, so let's do that. So we can maybe pick a test point in each region. maybe we have a 0 in here, maybe 1 over here, because square root of 2/3 is less than 1. And maybe we choose -1 over here. Okay, and then if we think about what happens when we plug these in, if I plug 0 in, I'm just going to end up with a 24 over, so I'll end up with a positive over a positive. So this one will be positive, right? You'll end up with a 24 over 2 cubed. Over here, you would get 24 minus 36 over 3 cubed. So overall, that's a negative, right? Because the 24 minus 36 is negative. And then over here, you would get also 24 minus 36 over. So you get exactly the same thing here. Cubed. So you get a negative here as well. Okay. And so one thing that this tells you is that because the concavity switches at minus root 2 over 3, this is an inflection point, and this one is as well. So these are inflection points. Okay. So now we've gathered all the information together, and we're going to try to piece together the graph. Okay. Well, so maybe one other thing we want to do here before we actually do that is it's nice to know what the actual values are at like inflection points and mins and maxes. So let's figure out like what is f of this. And maybe I'll save us a little work and just tell you what the answer is. It's 5/4. And if you do it at root 2 over 3, well, we should know that this is the same because the function's even. But these are both 5/4. So that gives us a couple more points on the graph. So let's go up here and put those in way up here. Okay, so let's go red. Okay, and so, minus, and we said it was what, 5/4, and this is 1. Wait, did I read the right thing? Oops, sorry, they're minus 5/4. Yeah, that makes more sense. So these are minus, I forgot a negative. Yeah, Jake, I am recording them and posting them on YouTube so that you can watch them later. But if something doesn't make sense to you, feel free to stop and ask. It is a lot of information, which is why I think this section is difficult. So now these are negative 5/4, which is bigger than -2. But let's just imagine they're in here somewhere. Maybe I can try to make them even. It's a little hard to sketch on this thing. Our graphs don't have to be perfectly accurate. As long as they have the right properties and, things are in sort of the right places, I'm okay with it. Okay, and so now, based on what we said before, like to the right of 2, if we look at this diagram, to the right of 2, let's get rid of these green things. They look like negative signs. To the right of 2, the function's increasing because of the plus. And to the left of 0, it's negative. And to the right of 2 from down here, it'll be concave down. Okay, so that means this little piece here should be concave down. Whoops, where did my point go? So it should be concave down, so maybe we draw something slightly like that. So it's increasing and concave down. Because this function is even, it's going to do exactly the same thing on the left. So we don't have to actually, oops, I hate when I do that. Where did my line go? Okay, around red. So it should do the same thing to the left. Okay, and now we have all these other little regions to worry about. So we know everywhere to the left of 0 it's increasing. So we know it'll be increasing in this this left part, or this right part. But we want to understand what's happening to the concavity. So the concavity is from this diagram. We know it goes minus, plus, minus, and it splits at the square root of 2/3s. So what that means in terms of the picture, it's hard to go back and forth between these, is so in the middle part it's concave up. So that means between these three all together have to be sort of a concave up function. I'm making it a bit messy. And then after the root 2/3s on the outside of them, they have to be concave down. So it's going to look something like this. And then this point here, these, right, this should be an inflection point. Maybe let's get rid of those too many arrows here. Okay, and that's our graph. All right. It's a little bit messy in the middle. If you wanted to, you could kind of go clear it up after you sort of understand what it should be. You know, sometimes like if you wanted a really nice sketch, you might have to do this twice. You know, have like initial messy sketch and then, you know, try to clean it up a little bit. But yeah, this is roughly what our function looks like. Okay. So any questions so far? So it's sort of like you sort of get a skeleton of what the function looks like from having the asymptotes and a few of these important points, and then your first and second derivative information tells you like how do you link them up, right? So it's sort of like a connect the dots sort of idea, but you have more ways to connect the dots than just straight lines, right? Okay. Okay, so yeah, that took a while. So why are the inflection points not on the same? So can you be a little more specific? So oh, I see, because I pointed at the wrong one. Yeah, the inflection point should be here. Yeah, you're right. So they should both be the root 2/3 ones. Yes, thank you for helping me catch that. So yeah, this part should all be concave down here. My left part looks kind of screwed up. My right part looks nice. And the left side should look like a reflection of that in principle. Okay, anybody else? Okay, so I think we only have time for one more, so let's get to it. So it's another one of these rational functions. I have another example I might post online if you guys want to see it. You know, this takes a lot of practice. So, you know, just do the best you can. I'm not going to give you the hardest functions in the world, unlike exams. But maybe something on the level of like these, if I give you the derivatives and stuff. Okay, so we're going to do essentially the same thing as before, but now we have this slightly different function, this one. And here again, I've given you the first and second derivatives already, so we don't have to waste time computing those. Okay, and now we go through exactly the same steps again. So I'm going to kind of skip step 0. You can think about it on your own. I'll tell you that it is an even function. But yeah, let's skip straight to the intercepts. So the x-intercepts would be when g of t, when the y value is 0. And what is the thing we're doing? Okay, here it is. So yeah, this would say 3t squared. When is this 0? And that's when the numerator is 0. And if you do a little algebra, you get that t squared is 7, so t is plus 7 or minus 7. Okay, so there's two x-intercepts. You get a plus 1 and a minus 1. The y-intercepts are easier. That's, you just plug in 0. Right, so when x is 0, y is what? Let's see, it's minus 21 over minus 1, so that's just positive 21. Sorry, wait, I shouldn't be saying x here, I should be saying t's. And t is 0. Okay. So that gives us a couple points on the graph, 3 points. So let's see. So on the graph, it would look something like, so when y is 0, it's up here somewhere at like 21. Oh, I forgot some square roots, right? Yeah, when you should actually square root both sides here, right? So these are square root of 7s, right? T squared was 7, so t should have been plus or minus the square root. But yeah, we just put these on the graph. So let's say root 7 is over here somewhere. Minus root 7 is sort of an equal distance on the other side. And so now we have 3 points on this graph. Okay, so that's the intercepts. Let's go and figure out, are there, what happens with the asymptotes? Does this function have any, and what are they? Okay. So let's first maybe do vertical asymptotes. Okay, so remember, a vertical asymptote can only, well, at least for a rational function, the only way it's going to happen is when the denominator is 0 and the numerator isn't 0. That's just about the only way. So here, these will come from when the denominator is 0, which would be this. So this will give you t equals 1 and t equals minus 1. Okay, so we have two vertical asymptotes. Let's put those on the graph. Oh, I went by the graph. Let's maybe put these in blue. So I said plus or minus 1. So that's smaller than root 7 by a bit. So let's say this is t equals plus 1. That one looks pretty crooked, doesn't it? Okay, then we have t equals minus 1. Those are our two vertical ones. Okay, let's then look at horizontal ones. So horizontal ones come from looking at the limits at infinity of the original function. And if you think about, just comparing the powers in the numerator and denominator, we see that it should be the ratio of the coefficients because both powers are t squared. So this will be 3 over 1, which is 3. And the limit at minus infinity is the same. For rational functions, if it's equal to a number, they always come out to be the same. But if it's like an infinity or something, they can be different. This one's also equal to 3. So this tells us that there's one horizontal asymptote of y equals 3. So so far we found these asymptotes. Let's draw in our horizontal one now. So y equals 3. I'm going to make it a little higher than maybe 3 would actually be so that we get a nice looking graph. The scales are never quite right on these things. That's okay as long as we get sort of the right shape. This is y equals 3. Okay, and then we ask ourselves again, can this function have any slant asymptotes? And just like before, this one has no slant asymptotes because the only way a function can have a slant asymptote is if the degree of the numerator is exactly 1 bigger. And these are the same. Okay, so we found all our asymptotes now. So you could go and figure out like what happens at each asymptote using limits. Like, so you could figure out like, does this come in from the top or the bottom? But we'll be able to figure that out another way, so I'm going to skip that this time. And I've showed you how to do some of that in the summary sheet solutions. You can look at that again. Let's skip to looking at the first and second derivatives. So the first derivative, what does that tell us? So let's copy down the first derivative first of all. So g prime of t was 36t over t squared minus 1 all squared. And the things we always look for when we're trying to figure out where it could switch sign is where is it either 0, where does it cross through the x-axis, or where is it undefined, like what are its vertical asymptotes and stuff. And in this case, it turns out that both of these cases happen. So in the first case, when is this 0? Well, it's exactly when the numerator is 0, and that's exactly when t is 0. So that's 1 point. Where it doesn't exist, on the other hand, would be when the denominator is 0. So that'll be t equals 1 and minus 1. Okay, so there's 3 points we have to put on our number line now. So the derivative in principle could switch at 0, at 1, or at minus 1. And now we have to check each region for what the sign is. So out here, maybe we choose like a point like 2, maybe a half, negative a half, negative 2, and we check like what the sign is, but if you'll notice, one nice thing here is that the denominator is always positive, right? Because it's squared. And so in the top will be whatever the sign of t is, right? Because 36 times t will either be positive if t is positive or negative if t is negative. So really it's only like if you plug a positive number in, it'll be positive. If you plug a negative number in, it'll be negative. So this is one of those cases where it doesn't switch back and forth between plus or minus like we've seen a lot. Okay. So when you're thinking about local mins and maxes, one thing that can be important, it doesn't actually happen here, but if you think about it, like -1 could never be a local min or max because the derivative actually doesn't exist here. So sometimes it's worth writing this. And that was because it's an asymptote. And the same at 1. The derivative actually didn't exist here. So even if it had gone like plus minus, then it wouldn't be a local max. But 0 was okay, because that just came from the derivative being 0. And so this one, the function goes down and then up. And so this will be a local min. Okay. So it might be worth going and putting that information on the graph, just the local min part. So we know at 21, at t equals 0, this is going to go up on both sides. Okay, and we'll come back and use the rest of the information after we've done the second derivative. Okay, so any questions about the first derivative stuff? Okay, well, let's repeat the same process essentially with the second derivative. So the second derivative info, let's copy down the second derivative. So the second derivative was what again? Let me find it. $36 cubed, like that. Okay, and we're looking for, where is this 0? Or where is it not defined? Okay, so the places it will be 0 come from solving this. Cubed, which will be exactly when the numerator was 0. No, I copied something wrong already. This should just be a 3. 3t squared plus 1, and that has no solutions. Okay. But there are places where that doesn't exist because the denominator can be 0. So that would come from when is t squared minus 1 cubed equal to 0. If I cube root that, we see that it's, t equals -1 and t equals 1. Positive 1 and -1. Okay, so, this is kind of nice. We only have 2 things on our number line. So we only have -1 and 1 again. Okay, and if we test each region here, maybe 2, 0, and -2. So that, this is a little bit more involved. Well, maybe not too much. But what you can observe here is that the numerator here is always positive. Okay, so you just have to worry about like what happens to the denominator. So the denominator is t squared minus 1 cubed. So we know that at like 2, it would be a positive number over 4 minus 1 cubed. And so that'll be a positive number. So overall, this one's a positive. Here, it'll just be a positive number, or possibly even 0, over just minus 1 cubed, which will be a negative number. So this is overall. Did I copy something wrong? I did. It doesn't affect too much until what we were just doing, but I forgot a negative when I copied it. So this is our second derivative is actually negative. So all these things are backwards of what they should be. So this part is all fine. This part is all fine because that didn't depend on the sign. But down here, we really have extra negatives in front of these. Okay. Okay, so that means we have to change this one to being a negative and this one to being a positive because this one's now negative, negative. And then over here on the left, it'll be negative of a positive on top over, well, because the minus 2 gets squared to 4, it actually ends up being the same, which we could have also known that from it being even. Okay. So now, what we learned from this is what? So you might think that minus 1 and 1 are inflection points, but they're not. So can anybody tell me why they're not inflection points? No? Well, remember, what was going on here? The second derivative didn't exist here. And that was because they were asymptotes of the original function. Right? So an asymptote can't be a point of inflection, right? Because the function actually has to go through the inflection point. So these are not inflection points, which is why I think it can be useful to keep track of like which ones, did your second derivative actually exist at, and when did the original function actually exist at. So all we really get here is the concavity. There are no inflection points. Okay. And now we try to put this all together in the graph. So let's remember this, that the second derivative went minus, plus, minus, and it breaks at plus or minus 1. And from the first derivative, it goes decreasing, decreasing, increasing, increasing. Okay. So at in the middle here, maybe I'll do the middle part here, it went decreasing, increasing, and it was concave up in the middle. All right, so that would be that sort of picture. On the outside, like to the right, it was increasing and concave down. So that sort of means it has to do something like this, and it has to go through our point. And to the left, it was decreasing and concave down, so that has to be something like whoops. It should go through our point if we can make it. Something like this. So this should roughly be what our graph looks like. And you should always go back and check, like, did it match all these pieces? Did it go decreasing, decreasing? So it did. It went sort of like decreasing, decreasing, right? And then it went increasing, increasing. It went concave, down, up, down. Okay. All right, so that's our graph. Anybody have questions on how this stuff works? I know it's a lot, and it takes practice. So like you have to go through some of these yourselves. Okay. Okay. So I think I'm gonna call class there today, give you a little extra time to complete your quiz. But I'll stick around for another 5 or 10 minutes if you guys have questions. Otherwise, have a good day, and I'll see you on Friday for our review.